Hello, I'm James Kretchmar, Vice President and CTO at Akamai Technologies. One of my responsibilities is to ensure the reliability of Akamai's global edge platform. We take reliability very seriously at Akamai. It's very important to our customers and it's important to us. And so we've implemented really a large number of sophisticated reliability technologies into the platform itself. And up until last year, it had been about 17 years since the last time that we had a service incident that had any significant global impact. But today I'm going to talk about an incident we had last year that did have significant impact. We're going to look at the technical underpinnings of why it occurred and what the lessons learned are for us going forward. Now, first, for those of you who are not familiar with Akamai, we have the world's most distributed compute platform from cloud to edge. Customers come onto our platform to make their applications fast, to make it reliable, to make it scale, and to protect their applications from the most sophisticated and largest attacks on the internet. Many of the world's leading sites are on the platform. You use us every day, even if you're not aware of it. Many familiar sites for e-commerce, for banking, for streaming video. We deliver those, and we do it at massive scale. On a typical day, we're serving over 175 terabits per second of traffic, and peaking to over 250 terabits per second of traffic. And those numbers continue to rise over time. But the most important thing is to understand that we do this by way of our very highly distributed edge platform. We have our servers deployed in over 4,000 locations around the globe and in 134 countries. And that's important for a few reasons. First, by being very close to the end user, that's the way that end users can get a really great fast experience. They're getting the content from a server very close to where they are, and most of the time in the same network. Second, that lets us protect the applications against massive attacks because we have a massive platform to absorb those attacks, in addition to looking for malicious types of activity. But the other thing is that this highly distributed platform has a real impact on the way that we think about and design the reliability systems for our platform. So let's turn to the July 2021 incident. This incident, it impacted only a percentage of our customers, but those customers were impacted for about an hour, and so it was pretty bad impact for them. Now, many of our customers, they come to us for our very long track record of reliability, and so this was outside their expectations of our reliability, and honestly, it was outside our own expectations of the reliability our platform is meant to provide. So we've undertaken a lot of activity to investigate and to ensure we won't have a repeat of the same type of thing in the future. And that's what we're going to look at here today, what went wrong and what we can do to prevent it. Now, before I jump into the details of the incident, let me give a little bit of background on the part of the technology that's relevant here so that you can understand the landscape. As I mentioned, Akamai has thousands of edge clusters deployed around the world, and within each edge cluster, there's many servers. But we're interested in a number of processes that execute in those edge clusters. We don't care too much about what servers they're running on. Now, when an end user makes a request for content from the Akamai platform, first, the browser has to do a DNS lookup for the host name associated with that content. And when they do that DNS lookup, it comes to one of our edge clusters to get an answer for the server IPs that should serve the content. And we do two magic things at this stage in the process. First, we're going to choose a set of server IPs that are from an edge cluster that's located very close to the end user and that we know is delivering good internet performance between the end user and the cluster. That's the way we get the really great performance out of the platform. But the second thing we'll do is we'll choose IP addresses of servers within the cluster that are the best ones for load balancing the content among the servers in the cluster. So once we've returned those server IPs to the client, it can then contact the HTTPS service in the cluster to receive the content. That HTTPS service, it actually provides load feedback to this load balancing component running in the cluster. And it's actually that load balancing component that was responsible for giving the content to server assignments to the name server process. So that's the landscape. That's what you have to understand as the technical starting point for the incident. The one other thing is that we do have an ability to push configuration out to our components. And we usually do that through a configuration safety stager. And I'll talk about that in a moment. And in this case, the core of the incident was a bad configuration that we pushed out to this load balancer process. And that's what we'll be looking at. So what went wrong? I'm going to look at 5 key areas of things that didn't work the way that we expected them to, that were meant to prevent an outage like this. First is bad config rejection. We didn't reject that bad config the way we would have expected to. Second is staged rollout. have a mechanism that tries to get configs safely out to the network, and it didn't work the way it was supposed to. There's a tooling dependency thing that's interesting here. I know that it's a common problem now for companies to have their own tooling using their own services that can prevent resolving an incident. We actually did pretty well with that, but it had an unexpected quirk to it that we didn't see coming, and I'll talk about that when we get to it. And then finally, some issues with alert signaling and rollback. Okay, so let's dive in. First, the bad config rejection. So as I said, the core of the incident here was a bad configuration that we pushed to the load balancer process. I'll skip for the moment why that bad configuration got through the config safety stager. I'll come back to that in a minute. But the bad config did get to the load balancer processes. Now, the configuration change we were making, it made use of a particular feature that we have that we can use in that configuration for the load balancer process. And that's a feature that lets us flexibly assign an internal load balancing ID to a given domain name that's retrieving content. Before we had this feature, that was just a fixed mapping, and now we have the ability to flexibly make a reassignment. You don't have to understand anything about the details of that. It's really just the existence of this feature that's important to be aware of. So we made a change that was using that feature, and the change, it was syntactically correct, but it was semantically incorrect. And semantic errors are often much harder to detect automatically than a syntactic error. But in this case, the load balancer process, it did recognize that there was a problem with this configuration. So that was good. The component, it took two actions in response to this problem. First, it reported the bad condition via telemetry. That's important, and we'll come back to that in a minute too. And second is it tried to fail back into a safe operating mode given that bad configuration. Now, this is something that we typically expect of our components, that they have a way to fail back safely in the event they receive a bad configuration. Typically, that would be to reject the configuration and use the previous one. And there's a lot of sophisticated ways to do that, to detect that you've got a bad config. Maybe you've crashed after receiving a config or crashed twice. But in this case, we had a different methodology for falling back to a safe mode. Now, this was implemented when we first rolled out this flexible assignment feature. And the methodology was that if there was a problem, to revert back to fixed assignments and not use that flexible assignment feature. We did this for complicated technical plumbing reasons. That's why we didn't use our usual method. We knew that, but we had a reason for doing it differently. The problem here is that that was safe at the time of first rollout of that flexible assignment feature. If we're adding a new config that uses that and it breaks something, then that's the only thing that won't work anymore. All the static assignments will stay operational. But now it's years later. We had put that in place before, and now we've got a lot of production traffic that is making use of that feature. And when this component had that behavior of going back to a safe mode, it resulted in content that made use of that feature on production use being unassigned for load balancing. That resulted in serve fail responses from the DNS process, and clients could not get to the content. So that's pretty bad. There's a pretty clear lesson learned from this. We have a methodology here for safety, but we need to make sure that that safety methodology is up to date and consistent with best practices. In this case, it wasn't, and that led to the incident. Now, that's not the only thing we're doing to try to prevent a safety problem. So as I mentioned, we've got thousands of edge clusters around the world, and each of them has an active load balancer in it. And one of the ways that we provide additional safety is by incrementally staging configurations out to the network. We have a component that's dedicated for this. I've called it here Configuration Safety Stager. And when we push a configuration to it, it can operate in one of two modes. Either an operator can manually push it from stage to stage, or it can automatically allow the propagation to stage out to the network, but it'll do safety checks along the way. So for example, we would typically send a new configuration to a small fraction of the network first, and then we get feedback from the network to understand if everything is healthy. If it's not, we will stop. In some cases, we'll automatically revert the configuration, and in all cases, we would alert an operator to the problem. But if things look good, we'll then propagate to a larger percentage of the network, but still perform safety health checks, understand if there's a problem, and if there is, we would halt or roll back and alert an operator. Now, unfortunately, what happened in this case is that configuration, even though there were bad things happening on the network, it did propagate out to the entire network. And the reason is we had a bug in the safety checks themselves. Now, there were two elements to this bug. The first is that it was configured in what I'll call a wait for good mode as opposed to a stop on bad mode. That means when it was looking at the network, it said, things don't look good, so I'm going to wait until they do in order to proceed to the next stage. Now, given that things weren't looking good, this by itself wouldn't be a problem. This would stall the propagation of that configuration. The problem is there was a second problem with the safety test, which is that it was using a reporting mechanism for a bad configuration that stopped reporting the bad condition after a fixed amount of time. It kind of cleared the error. Now, these two things together are deadly. The test was waiting for a good condition to occur. We stopped reporting the bad condition. It thought everything was fine, and so it continued propagating out to the network until it got everywhere. We had safety improvements to these checks in progress. Unfortunately, they weren't complete yet at the time of the incident. But even so, this clearing behavior of the errors, that wasn't something that we really fully understood the impact of. And so we had a problem there anyway. So there's a clear lesson learned here. The staged rollout, it's only as good as the safety checks themselves. So we need to make sure that the safeties are well maintained, that they're up to date, and that they're consistent with best practices. Let me talk about the tooling dependency. Now, we had something in this incident where we have many of our internal tools configured to use our own service. We want the same type of scale and reliability and security that we're offering to our customers' applications for our own internal tooling. Now, that did result in some initial delay in debugging what was happening during the incident. The good news here is we had been concerned about that type of problem for a very long time, and so we did have procedures in place to route our applications directly and off the platform in the event of an incident that made them unavailable. The other good thing here is that we executed that procedure pretty early on in the incident, and so we were able to use our normal tooling. The thing that was a little bit of a strange quirk here that we didn't expect is that because the internal tools started working at a point during the incident, some of our staff took that to mean that maybe the incident had actually been resolved for everyone. It hadn't been clear to them that this was just a partial point resolution because we had taken an operational step to make the tooling work. So there is a little lesson coming out of that. These important operational steps taken during an incident, we need to have good communications on that going everywhere. Typically we do. In this case, it was operated by one team that doesn't integrate with those communications the same way, and that's something that we fix going forward. Let me talk about alert signaling. We did have alerts fire on the network as we were rolling this configuration out that told us that there was an unusual amount of serve-failed DNS responses being given to end users. Now, the trouble with this, though, is that because it was during the staged rollout, it was only small fractions of the network that were reporting this error condition. And we did not have a tight coupling between the rollout staging path and the alerts that we were getting back. So it wasn't clear that it was all of the staged areas, the incremental rollout that was failing. We just thought it was a small percentage of what was happening on the global network. That's a miss. If we had known that it was specifically those staged rollouts, then we would have been able to quickly determine it was because of this configuration rollout, and we could have halted it in time. But we didn't have that, and so the configuration propagated out to the world. At that point, it did fire priority 1 alerts for all of this bad responses that we were giving, and then it was pretty easy to determine what was responsible for it and to roll the configuration back. But we have a learning there about a consistent coupling between the alerts and the staged rollouts. That's something we usually have in place, but we didn't in this circumstance. Finally, let me talk quickly about rollback. As I said, once we got the P1 alerts and it was clear what was happening, we went to immediately roll back the configuration to a last known good, and an operator did that. In this case, usually we can do that immediately. We did have a little bit of a delay here because of a UI and tooling issue on the configuration safety stager. It didn't contribute to the majority of the delay here with the incident, but it did contribute some. And so it fixed the problem when we rolled it out, but we have a learning here that we need to make sure that that immediate rollback is really fast and easily available at all times. So where does this all land us? What's the big takeaway from this for us? We have a methodology and a system where we put multiple layers of safety in place, but still we had an incident. And any one of these things would have prevented that incident. If we had had the better bad configuration rejection, we wouldn't have had an incident. If we had had better staging checks, we wouldn't have had the incident. If we had had alerts coupled directly with the rollout path, we probably wouldn't have had the incident. All of these things had to come together to fail, and they all did. Now, for us, we place a heavy focus at design time on preventing things like component interaction failures, cascading failures, congestive collapse types of failures. But none of that does any good if we haven't ensured that the underlying safety mechanisms have the same rigor applied to them as the systems they protect. And we'll do that as much as possible via common underlying safety mechanisms when we can, but where we can't, we do need to have governance to make sure that those things are where they need to be. And that's one of the major things we've done coming out of this incident is added new governance to make sure that our safety systems are receiving the same rigor and attention as the primary systems. Now, let me add one more comment before I go. These incidents, they're not at all fun. They're very painful for our customers. They're very painful for us. They're painful for our customers and users. But I do think that there is one positive thing that comes out of a situation like this. And that's that it demonstrates to us how critically important the internet has become. Even a relatively small outage is really important to avoid. And what I'm happy to see is that at events like these, we can have industry-leading companies come together to look at ways to prevent outages in the future. And I really think that over the next 5 to 10 years, there'll be a lot of important work in making the internet more reliable for everyone. Thank you.